Hello class, I hope you're having a wonderful day. Today I would like to take a look at one of our practice problems from Chapter 8 where we are required to calculate an object's moment of inertia, its angular acceleration, the net torque applied to a pulley, and the net force applied to a belt that is moving the pulley. So let's go ahead and get started. A solid steel pulley has a mass of 15 kilograms and a diameter of 0.44 meters. The pulley is initially at rest and accelerated to 8 revolutions per second in 15 seconds. So we have 4 parts to the problem. Part A is calculating the angular acceleration of the pulley. B is the moment of inertia of the pulley. C, the net torque applied to the pulley, and D, the net force applied to the belt that will rotate the pulley. So what we need to do is create a column of knowns. So starting out, the mass of the pulley is 15 kilograms. So I'm just going to say M sub pulley, 15 kilograms. The diameter of the pulley, so I'll use the diameter symbol, is 0.44 meters. And we know that the radius is half of the diameter, so the radius of the pulley is 0.22 meters. The pulley is initially at rest, and so our initial angular velocity, so we're going to use the lowercase Greek letter omega here, so omega sub I is equal to 0 radians per second, so it's at rest. And then it says it's accelerated to 8 revolutions per second in 15 seconds. So our final angular velocity is 8 revolutions per second. Okay, now we're going to need this in units of radians per second. Right now it's in revolutions per second. Now we know the conversion, 1 revolution is equal to 2 pi radians. Okay, so we're going to perform some dimensional analysis here. So I've got 2 pi radians in 1 revolution. Our units of revolutions will cancel. So 8 times 2 pi and I get 50.265 radians per second. So that is our final angular velocity and our time interval. So we're going to start with an initial angular velocity of 0 radians per second. We're going to accelerate the pulley. So we're going to accelerate it for a time of 15 seconds, and at the end of the 15-second time interval, our final angular velocity is 50.265 radians per second. Okay? So in part A, let's calculate the angular acceleration of the pulley. So I'm going to say alpha sub p. So this is going to be the change in the angular velocity divided by the time interval. So in the numerator, this is going to be the final angular velocity minus the initial angular velocity, and once again divided by delta t. So in my numerator, we've got 50.265 radians per second minus our initial angular velocity, which is 0 radians per second, and we're going to divide this by 15 seconds. So this should be slightly greater than 3. I've got 50.265 divided by 15. And that gives me 3.351. And let's take a look at our units here. I have radians per seconds, and this is seconds over 1. And you know the old algebra rule that says whenever we're dividing fractions, it's like multiplying by the reciprocal of the denominator. So this is going to be radians per second times 1 over seconds. That will give us units of radians per second squared. Okay, I'm going to write that value over here in my answer column. So the angular acceleration of the pulley is 3.351 radians per per second squared. Okay? Now, we need to calculate the moment of inertia of the pulley, identified by capital I. All right, so I sub pulley. So for geometry of a pulley, so we have a cylinder here, and we have a radius. So our radius is 0.22 meters, and here is our axis of rotation. So for this type of geometry, we're going to have 1/2 times the mass times the radius squared. And remember, for rotational moment of inertia, the distribution of the mass with respect to the axis of rotation is actually more important than the mass itself, okay? So what we have is 1/2 times the mass, and the mass is 15 kilograms, times the radius, 0.22 meters, and that quantity is squared. Okay, so I've got 1/2 times 15, that's going to be 7.5. So 7.5 kilograms times 0.22 squared is going to give me 0.0484, and we have units of meters squared. Remember, not only do we have to square the numerical value, we also have to square the unit value. So we're squaring that and that. Now let's take the product of these two values here. And this is going to give me 0.363 kilogram meters squared. So I'm going to copy our answer down for the moment of inertia of the pulley. I'm going to put it in my answer column over here. 0.363 kilogram meters squared. Okay? Going to erase this. Okay, next, the problem wants us to calculate the net torque applied to our pulley if we have an angular acceleration of 3.351 radians per second squared. So what we're going to do here is use Newton's second law for rotational motion. Newton's second law for rotational motion. Okay, so that's going to be the angular acceleration of an object is directly proportional to the net torque applied to the object, and it's inversely proportional to the object's moment of inertia. So what we have here is the angular acceleration of the pulley is equal to the net torque applied divided by the moment of inertia for the pulley. So we're going to isolate net torque. So what I'm going to do is multiply both sides of the equal sign by moment of inertia for the pulley. So what we have is net torque is equal to angular acceleration times moment of inertia for the pulley. We're going to use the calculated value for both of these variables here. I've got angular acceleration, 3.351. Radians per second squared times 0.363 kilogram meters squared. Okay, now we're going to take the product of these values here, and remember that the radian is a derived unit, so it's not going to be quoted in our answer. We're not going to carry it into our answer. So I've got 3.351 times 0.363, and we have 1.2164. So I've got radians per second squared. We're not carrying the radians into the answer since it's a derived unit. This is kilogram meters squared, and algebraically we know that's over 1. This is going to be kilogram meters squared per second squared. Okay? Now what I want to do real quick is talk about some units here. I want to factor out a meter in this unit here. So what I've got is a kilogram times a meter per second squared. And I'm factoring out a meter, so times meter, okay? Now we know that a kilogram meter per second squared is equal to 1 Newton. So what I have is a Newton times a meter. And whenever we're quoting torque, it's always described with units of Newton meters. Okay, so what I've got is 1.2164 Newton meters. Okay, there we go. I'm going to erase the board here. I need to free up some room. Okay, moving on. Next, the problem wants us to calculate the net force applied to our belt. And when we apply a net force to this belt, it's going to cause the pulley to rotate about the axis of rotation. So here we've got something that looks like this. Here's our axis of rotation. Okay, so we know that net torque is equal to our perpendicular applied force. So this is F sub A times sine theta times our lever arm, which is identified by R. This is going to be the radius that the force is applied with respect to the axis of rotation. Okay? Now, looking at my picture here, we're pulling straight down, and so this is going to be a perpendicular angle right here. Okay? So what I have is net torque is equal to our applied force times sine of 90 degrees times our lever arm of 0.22 meters. Okay? Now we know that sine of 90 degrees is equal to 1, so what we're doing is maximizing our torque by applying a force in a perpendicular direction. So sine of 90, this guy goes to 1. Okay? So now what I have is our applied force times our lever arm. We're going to isolate our applied force by dividing both sides of the equal sign by our lever arm, which is 0.22 meters. So what I have is applied force is equal to our net torque applied to the pulley. We're going to use our calculated value right here. I've got 1.2164. We have units of Newton meters. We're dividing by 0.22 meters. And as you can see, our units of meters are going to cancel, leaving us with units of newtons. And that's great because you know in the metric system, the units for force are in newtons. Okay? So I've got 1.2164 divided by 0.22. And this will give me our applied force is 5.529 newtons. Okay? All right. So that is the answer to part D. Okay? If you have any questions, as always, you can give me a call, you can send me an email, or you can contact me over Canvas. But I hope me walking through this problem today has helped you out, and I hope you have a wonderful day.